A very good morning to all of you. In the previous class, we dealt with the topics basic working principle of DC motor, their power equation and their torque equation. Today we are going to study about various characteristics of different types of DC motors and their applications. It is this characteristics which makes a particular DC motor suitable for a particular application. Basically, the motor characteristics are classified into three. They are actually torque versus armature current characteristics. It is also known as electrical characteristics. It is actually the armature torque versus armature current. The second characteristic is the speed versus armature current, and the third characteristic is speed versus armature torque. It is also said to be mechanical characteristics. These characteristics are determined based on the two relations, that is speed is equal to K into EB by phi. From here we can say that speed is directly proportional to EB by phi and armature torque is directly proportional to phi Ia. This particular relation can be obtained from the standard relation of back EMF, that is back EMF is equal to phi P and Z by 60A, and this particular relation can be obtained from the standard relation of armature torque which we have derived in the last class, that is armature torque is equal to 0.159 phi Z Ia into P by A. We will begin with characteristics of DC series motors in detail. There is no need to by heart all these characteristics. You just need to remember the standard relations, then you will be able to determine the characteristics by yourselves. This is actually the electrical characteristics of DC series motor. From the standard relation we very well know that armature torque is directly proportional to phi Ia. In the case of a DC series, hence Ia is same as that of If, that is armature current is same as that of the field current. Basically this phi is directly proportional to the field current. In the case of DC series motor, field current is same as that of the armature current, hence I can say that the magnetic flux is directly proportional to that of the armature current. This direct proportionality between the magnetic flux and the armature current will occur only before the magnetic saturation region. Once after the magnetic saturation is achieved, phi does not has any dependency over the armature current Ia. So it's very clear that before the magnetic saturation region, phi will be directly proportional to Ia, and once after the magnetic saturation is achieved, phi will not have any dependency over the armature current. Now let's apply this in the basic torque relation, that is armature torque is directly proportional to phi Ia. Now if you see in this characteristics, the curve is actually a parabola for very small values of Ia. This is because for this very small values of Ia, the region comes under the magnetic saturation region, hence phi is directly proportional to Ia. Since phi is directly proportional to Ia, I very well can say that armature torque is directly proportional to Ia square. As armature torque is directly proportional to Ia square, hence I can say that armature torque versus Ia will be having the shape of a parabola. See, if you see after this particular value of armature current, the characteristics will be almost linear in shape. As the value of armature current is increased, the field current will be increased and the field poles are of a position above the magnetic saturation region. Once if the magnetic saturation is achieved, the magnetic flux will not have any dependency over the armature current. That is, the armature torque will be having dependency only over the armature current, that is TA is directly proportional to Ia alone. Therefore the characteristics between the armature torque and armature current will be having a linear shape. So this initial portion of very small value of armature current indicates that the region is below the magnetic saturation. As this region is below the magnetic saturation, phi is directly proportional to Ia. Hence therefore I can say that armature torque is directly proportional to Ia square. So if you plot the graph between TA and IA, for the very small values of armature current, the shape will be almost parabolic, and for larger value of armature current, the shape will be almost linear, as this armature torque is directly proportional to armature current. In this particular characteristics, the shaft torque is also drawn. From this characteristics, it is very clear that the magnitude of shaft torque is definitely less than the armature torque. This reduction in the value of shaft torque from armature torque is decided by the stray losses. That is, the responsible factor for this reduction is magnetic losses and mechanical losses associated with the DC motor. Hope the electrical characteristics of DC series motor is clear for you. Now we are moving to the next characteristics, that is speed versus armature current. From the standard relation of back EMF, we very well know that speed is directly proportional to EB by phi. Using this particular relation, we are going to determine the characteristics between speed and armature current. Just like we have considered the electrical characteristics, we will start with the small values of armature current in this characteristics also. When the magnitude of armature current is very small, then for this very small values of armature current, the magnitudes of back EMFs are also very small. That is, from the standard relation of back EMF, we know that back EMF is equal to V minus IaRa. When the magnitude of Ia is very small, definitely it does not have much influence over the value of back EMF, which can be obtained by using the relation V minus IaRa. So for small values of armature current, the speed will be having dependency only over the flux. That is, from the standard relation, speed will be inversely proportional to flux. The standard relation is speed is directly proportional to EB by phi. For very small values of armature current, there will not be any significant change in the value of back EMF. So we can say that speed will be inversely proportional to the magnetic flux. As we all know that the magnetic flux in the case of a DC series motor is directly proportional to that of the armature current. So from there I can say that speed is inversely proportional to armature current. So if you see in this characteristics, for very small values of armature current, the magnitude of speed is very large. Therefore it is said to be that a DC series motor should never be started under no load condition, because under no load condition the motor will be running, or the motor will be taking only a very small magnitude of armature current from the supply. Corresponding to this small value of armature current, the speed of the DC series motor will be dangerously high. It can be analyzed from this characteristics also. When the magnitude of armature current is small, the speed is very large. In order to avoid such troubles, it must be confirmed that a DC series motor should be started only under loaded condition. So far I have mentioned about light load conditions or very small value of armature current. Now let's consider the case of high value of armature current, that is heavy load condition. At heavy loaded conditions, definitely the magnitude of armature currents will be large. As speed is inversely proportional to that of the armature current, therefore for very large values of armature current, the speed will be low. This small values of speed at the larger magnitudes of armature current will cause the back EMF to be a smaller value. This is from the standard relation back EMF is equal to 5PNZ by 60A. Consequently, this reduced value of back EMF will further cause the magnitude of armature current to rise from the standard relation IA is equal to V minus EB by RA. So it's very clear that at large load conditions, the magnitude of armature current will be large, and this large magnitude of armature current will cause the speed to get reduced from the standard relation speed is directly proportional to EB by phi. This large load condition will also have influence over the back EMF. At this large load condition, when the magnitude of speed reduces, the value of back EMF also gets reduced. This will further cause the armature current rise from the standard relation Ia is equal to V minus EB by Ra. Next we are going to see the speed versus armature torque characteristics. It is actually the mechanical characteristics, and this characteristic seems very much similar to that of the speed versus armature current characteristics. In this characteristics it can be seen that when the magnitude of speed is high, the value of armature torque is very small, and vice versa, that is when the magnitude of armature torque is large, the value of speed is very small. This particular phenomena was very well explained in the last video session in this slide. Please go through that. The theoretical explanation which we have mentioned so far is also written here. You can go through it. In the case of a DC shunt motor, the magnitude of field current always remains constant. This constant value of field current will result in a constant value of magnetic flux. Therefore, from the standard relation of armature torque, that is thia is equal to 0.159 phi z Ia P by A, we very well know that thia is directly proportional to phi Ia. Since in the case of a DC shunt motor, as the magnitude of field current is constant 1, definitely the magnitude of flux also will be a constant 1. Therefore, thia will be having only direct dependency on the armature current, that is thia is directly proportional to Ia. Hence, if you are plotting the characteristics between thia and Ia, we will be definitely getting a straight line, that is a linear graph. Shunt torque characteristics is also plotted here. Just like what we mentioned in the case of a DC series motor, the magnitude of shunt torque will be definitely smaller than that of the armature torque. This is caused due to the effective stray losses which are present here. Stray losses is actually the sum of mechanical loss and iron losses. Next we are moving to the speed versus armature current characteristics, that is speed versus Ia characteristics of a DC shunt motor. From the standard relation of back EMF, we very well know that speed is directly proportional to Eb by phi. In the case of a DC shunt motor, the magnitude of phi remains constant. Therefore, speed will be having only direct proportionality over the back EMF, that is speed is directly proportional to back EMF. Or else I can say that speed is directly proportional to V minus Ia Ra. That is the relation for back EMF. Eb is equal to V minus Ia Ra. Therefore, I can easily say that speed is directly proportional to V minus Ia Ra. So practically, if you are trying to increase the magnitude of armature current or under the condition of high load, there will be a small dip in speed. This is due to the armature resistance drop in the relation of back EMF, that is speed is directly proportional to V minus Ia Ra. As we are increasing the magnitude of Ia Ra drop will increase. This will cause the overall value of V minus Ia Ra to reduce. But this reduction in speed due to Ia Ra drop seems to be a very small one, which is less than even 5 to 15%. Therefore, we can say that a DC shunt motor is almost a constant speed motor. The line shown here in the blue color indicates the ideal characteristics of a DC shunt motor, but the actual characteristics will be like this. Since as we are moving from light loads to heavy load condition, as there is no considerable change in the case of speed, we can say this DC shunt motor can be used for constant speed applications. We have clearly seen in the case of a DC series motor from their speed versus armature current characteristics that a DC series motor should never be started under no load condition. While coming with the DC shunt motor, it is clear from their speed versus armature current characteristics that this particular motor can be used only for constant speed applications. This is actually the mechanical characteristics. Please note the change. Here it won't be Ia, this will be TA, that is the armature torque. As we have told in the case of a DC series motor, the speed versus armature torque characteristics will be very much similar to that of a speed versus armature current characteristics. Next we are going to study about the various characteristics of compound motor. In the video session of types of DC generator, I have explained that the compound generators were classified into two. One was cumulatively compound and the other one was differentially compound. In the same manner, the compound motor also can be classified into two, that is cumulatively compound and differentially compound. If the flux produced due to the series field and shunt field are aiding, that is if both the fluxes produced by series field and shunt field are in the same direction, then it is said to be the cumulatively compounded DC motor. And if the fluxes produced by both these field windings are opposite, then that particular motor can be said to be a differentially compounded one. The characteristics of cumulative compound DC motor lies exactly in between that of series motor and shunt motor. Just like that of the series motor, the cumulative compound DC motor is also having the ability to develop large amount of torque at very low speeds. But the best part is, cumulative compound DC motor can be made to run at either light load or no load condition. This is because of the shunt winding present in the cumulative compound DC motor. In the case of differential compound DC motor, both these fluxes are acting opposite to each other. So when the load current is increasing, definitely the magnitude of armature current will also increase. This further causes the current which is flowing through the series field winding also to increase. Therefore, the resultant flux gets reduced when we are trying to increase the value of load current. In the case of this series motor, the characteristics between armature torque and IA was TA is directly proportional to IA square. In the case of shunt motor, it was just like TA is directly proportional to IA. While coming to the case of differential, the armature torque is directly proportional to phi IA is the standard relation. When you are trying to increase the value of IA, definitely the magnitude of phi is getting reduced. Thus, you can't expect a proportional increase in the value of torque when you are trying to increase the value of IA. That's why the characteristics of differential DC compound motor is lying beneath the characteristics of shunt DC motor. Now let's see the speed versus IA characteristics of this cumulative and differential compound DC motors. Just like as we mentioned here also in the case of cumulative DC motor, the characteristics lies in between that of series and shunt. While considering the case of differential compound DC motor, as you know, when we are trying to increase the value of load current, definitely the magnitude of flux will be reducing. From the standard relation of speed, you know very well that speed is inversely proportional to the flux, that is, speed is directly proportional to EB by phi. In the case of differential compound motor, when you are trying to increase the value of IA, definitely the magnitude of flux is getting reduced. This causes the speed to further increase, as the speed term is inversely proportional to that of the flux term. Speed versus torque characteristics is very much similar to that of the speed versus IA characteristics. Another important point which you must remember is in the case of differential compound motor, if you are trying to run the machine at full load condition, in the case of full load, definitely the magnitude of armature current will be very large. Hence, therefore, the value of flux will be very, very small. This will cause the speed to increase to a very large value. That is, at full load condition, in the case of a differential compound motor, this motor tends to run at a very, very high speed, which is actually not a suitable condition. Therefore, the practical applications of differential compound DC motor is limited. Next, we are moving to the last topic of today's session, that is applications of these various DC motors. In the types of DC generators video session, all of you have studied about the applications of DC generators. Here we are going to study about the applications of DC motors. The applications of a particular type of motor is decided by their characteristics. Let's see, in the case of shunt motor, the motor is almost running at a constant speed condition. So it is also said to be a constant speed motor. Therefore, it is mainly used in applications where constant speed is required. That is lathes, centrifugal pumps, machine tools, reciprocating pumps, etc. Next is series motor. All of you are very aware from the characteristics of series motor that they are having very high starting torque. as TA is directly proportional to IA square. Therefore, they are mainly used in applications where high starting torque is required, that is for traction work, electric locomotives, trolleys, cranes, etc. Differential compound DC motor is having very limited use because when you are trying to run that machine under the loaded condition or under the rated condition, the machine speed will be very high. So you don't need to know about the applications of a differential compound motor much into detail. Now let's see the applications of cumulative compound DC motor. With this you can achieve variable speed, high starting torque, and this a variable speed is the main characteristics of series DC motor also. So almost the application also seems to be same. In specific, they are used in rolling mills, ice machines, printing presses, air compressors, etc. Even though they can produce high starting torque, it is not as high as that of produced by the series DC motor. Hence, they cannot be used for traction work or electric locomotives. With that, we are completing today's session. Thank you.